Of all substances on Earth, the simple molecule water is one of the most important for all life. This statement applies to the water of our external surroundings, known as the hydrosphere, as well as the water within living organisms. About 71% of the Earth's surface is covered by water, lakes, streams, groundwaters, and, of course, the oceans. We might infer that this simple compound of hydrogen and oxygen is important to life solely on the basis of its abundance in the biosphere. But even more significant is the remarkable fitness of water for the conditions of life within and without the living organism. No other substance even approaches water in appropriateness of its properties to living organisms and their interactions with their surroundings. While a biologist may look at an organism and ponder its adaptability to its environment, let us, as chemists, turn this question around. What is there about the environment, water in this case, that makes it so specially fit to support life? We need to examine 5 of water's properties to help understand its fitness. Those properties are heat capacity, heat of vaporization, densities of ice and water, surface tension, and solvent properties. Water's thermal properties are uniquely suited to moderate temperature. The heat capacity of liquid water is defined as the amount of heat, in calories, needed to raise the temperature of 1 gram of water, about a half a thimbleful, 1 degree centigrade. This amount of water, for a 1 degree change, requires 1 calorie of heat energy. Most other substances have lower heat capacities than water. This means water tends to absorb a lot of heat compared to other substances before its temperature actually changes. Now, temperature is one of the most critical factors affecting life on Earth. Anyone who has experienced a high fever, just a few degrees warmer than normal, knows this. Although man has devised ways to protect himself from temperature extremes, most organisms can survive only within a narrow range of environmental temperature. The high heat capacity of water tends to minimize temperature fluctuations, especially in large bodies of water. Fish and other aquatic animals rarely have to tolerate large temperature changes. Large bodies of water also moderate the climate of surrounding land. Compare the summertime temperatures of San Francisco with California's scorching Central Valley. Another way in which water moderates temperature is by virtue of its extremely large heat of vaporization. It requires 540 calories of energy to convert 1 gram of water to 1 gram of steam at 100 degrees centigrade. Most other substances have much lower heats of vaporization. Even more than the high heat capacity, it is the heat of vaporization and its reverse, the heat of condensation, that stabilize the temperature of organisms and their environment. Every gram of water evaporated absorbs 540 calories of energy, and when that water vapor condenses back to the liquid, those 540 calories are released. So in tropical areas receiving lots of sunshine, Every 14 drops of water that evaporate absorb 540 calories of solar energy, helping to cool that region. Winds then blow the gaseous water to cooler climes where the vapor condenses, and the droplets coalesce to form clouds. As soon as that gram of water vapor condenses back to the liquid form, it releases the 540 calories absorbed at the equator, helping to warm the region. A chart which compares marine temperatures and continental or inland temperatures clearly reveals water's moderating effect. Note that at 0 degrees latitude, the equator, the average continental temperature is 34.6 degrees centigrade, but the average marine temperature is 26.1 degrees centigrade. At the poles, latitude 90 degrees, the average continental temperature is minus 26.1, but the marine climate is minus 8.7 degrees centigrade. As mentioned before, it is particularly important to protect the complex molecules of life within an organism from temperature change. Water makes up 80 to 90% of the weight of the cell, the fundamental unit of life. So, while water's high heat capacity makes internal temperatures resistant to temperature change, evaporation of water is a particularly efficient way that perspiring animals and transpiring plants cool themselves. Every gram of water that vaporizes removes about 540 calories of heat from the organism. This pipe cracked when the water in it froze overnight. Water expands when it freezes. The solid phase is less dense than the liquid phase. In other words, ice floats. Very few other substances share this rather unique property, which again affirms water's fitness to support life. Because ice floats, bodies of water freeze from the top down, not from the bottom up. The top layer of ice insulates the underlying water from heat loss to the atmosphere, thus slowing down the further freezing of the body of water, allowing aquatic life to survive through the winter. Because water is most dense at 4 degrees centigrade while still a liquid, every autumn convection currents bring cooler oxygenated water to the bottom of the lake and bring the warmer, nutrient-rich bottom water to the surface. Of course, the expansion of water on freezing is an important tool in the weathering of rocks. The shattering of rock by frozen water aids erosion, one of the primary agents for soil formation. The surface tension of water is extremely high compared with most other substances. Surface tension is directly linked to the ability of the fluid to be drawn up in fine tubes, a phenomenon called capillary action. Plants in this way receive their nutrients dissolved in water and drawn up through the tiny fibers of their roots. Water has been called the universal solvent. Indeed, it has carved much of the Earth's land surface. But water is also capable of dissolving the myriad of compounds which keep life going. As a solvent, water plays two major roles within organisms. It acts as the transport medium for molecules and ions containing nutrients and regulatory substances that circulate among cells, through cell walls, and within cells. Furthermore, water participates in most of the biochemical reactions occurring in organisms. This participation is possible because water can ionize substances, and the resulting ions are required by cells for their energy-producing processes. The chemistry of living systems is largely developed around water's solvent properties. To understand why water has so many unique features which make it so fit to support life, we have to examine its bounding. The water molecule has two hydrogen atoms, each bound to an oxygen atom. The essence of these hydrogen-oxygen bonds is the sharing of a pair of electrons between each hydrogen atom and the oxygen atom. The electron distribution is represented symbolically here by the black dots.